this question, we're being asked to find the local maximum or minimum, or whether it's a saddle point. So we've got our two variables, and what we need to do is we find the first derivative, first partial derivatives, and where those are zero, we either have a minimum or a maximum, or a saddle point could be. And we'll use the second derivative test to figure out once we have those critical points. So first thing we need to do is get the partial with respect to x. I'm inventing my own notation here. Let's get it all in one color. So the partial with respect to x is going to be 2x. This becomes 0 because it's just a constant. You treat y as a constant, and then it'll be minus 5y. So it's a partial with respect to x, a partial with respect to y, the x squared, that derivative 0, and so then we get 3y squared from this term, that's its derivative, and then derivative of y here gives us minus 5x. Now these are both equal to 0, and so we can solve these simultaneously. We could solve this equation here, and remember the partials are equal to 0 means that the slope of that point is 0, so we've got a minimum. That's critical points. We have a minimum or a maximum. Okay, so this one we could solve. We get 2x equals negative positive 5y. Add 5y to both sides and then divide by 2. So x is equal to 5 halves y. What we can do with this now is plug that into this equation. So then we get, because this is also equal to 0, right? So that gives us 3y squared minus 5 times 5 halves y. That's what we're plugging in for x equals 0. That is 25 halves. And the best way to solve when you've got a quadratic is to factor when quadratic equal to 0. So we factor out the y, leaving us with 3y minus 25 halves equals 0. So this gives us two answers. So either y equals 0 or 3y minus 25 halves equals 0. So this one we're done. We got one solution. We'll plug back into x. And actually, if you plug it back here, you see if y is 0, then x is 0. So that gives us one critical point. So this, if y is 0, then x is 0. So we've got 0. 0 as one critical point, and then we should get the other critical point from here. We add 25 halves to both sides, so that gives us 3y equals 25 halves. Divide both sides by 3, or multiply both sides by 1/3, right? So we get that y is 25/6. So now when we plug that back in over here, we get that x equals 5 halves times 25/6. We're going to get that x is equal to 125/12. So the other critical point is 125/12 25/6. So those are our critical points. So So to understand what's happening at those critical points, we use the second derivative test. And what is the second derivative test? From our notes from Chapter 15, the second derivative test for functions of two variables. So we're told that we use this discriminant, which is the second derivative with respect to x, second derivative with respect to y, minus xy, second derivative squared. So this is at the particular point, this is the discriminant. And then we check all these cases. If the discriminant is greater than 0, then there's two possible cases. Then we look at the sign of the discriminant, the second partial with respect to x. And so it's either a minimum or a maximum in that case. If the discriminant is less than 0, then we have a saddle point. And then if the discriminant is equal to 0, then we really don't know anything. Okay, so let's calculate that discriminant using this formula. So we've got to get the second partials. Okay, so we're going to build off of these partials here, and then use that discriminant. So let's switch colors a little bit so we know we're doing something new. A little bit of green. Okay. Give me maybe a little bit more room. So the derivative of x, the second derivative of the partial of x, is going to be 2. That's it. Let's do the second partial of y. So we come to this one. That's going to be 6y. And then kind of cutting it off there, right? It's just going to be 6y. 2 comes down, minus 1. This is 0. Okay. Now, what do? We take the second partial of x with respect to y, or y with respect to x, and you'll see you'll get the same thing. It's x with respect to y, we're going to get negative 5. If you do y with respect to x, you also get negative 5. That's kind of cool. So this is negative 5, and so is the other one. So what is the discriminant? The discriminant so it's maybe good to have these printed out. Your notes, the discriminant is fxx times f of yy, second derivative of y, minus this. So multiply these two, subtract the second one squared. So let's see if we can. Okay, so the discriminant is going to be equal to fxx at the particular point as well. So we're going to use these 2 points, fyy minus fxy squared. Okay, so the discriminant becomes 2 times 6y minus negative 5 squared. So that's 25. That's minus 25. This is 12y. So we've got 2 critical points to check. So let's check at 0, 0. The discriminant is going to be equal to 0. It's going to be negative 25. Okay. So you plug in 0, 0 there. Okay. Get that. And according to this one, the discriminant is negative. We've got a saddle point. So, oops, where did they go? Saddle point. So this is a saddle point. let's check the other one, what happens. So let's check that point, 125, 12, 25 over 6. And again, all we're plugging in is the y values, so that gives us that the discriminant is now going to be 12 times 25 sixths minus 25. So that goes in there, that's 2, that's 50, minus 25. Our discriminant is actually now positive 25. So our discriminant is greater than 0. So what does the test say? Discriminant is greater than 0, one of these. So now we need to check the second partial with respect to x. Is it positive or negative? Well, remember ours is positive. X, our second partial is 2. 2 is greater than 0, so we have a local minimum. We have a local minimum. And so then we take f of x. X is also greater than 0, so this is greater than 0. So that tells us with these two things that this is a minimum. Two ends. Minimum. It doesn't look right. Probably one end. Minimum. I'll just abbreviate. Yeah. Okay, so that's a minimum. And again, you could check it by plugging it in, and you see it's not going to be, it's hard to tell. Is it a, well, they ask, let's see, minimum, maximum, or global maximum minimum. If we know it's a minimum, is it a global minimum? Well, we'd have to kind of evaluate this at other points to see if we get more minimum than we do plugging this in. It'd be nice to have a three-dimensional calculator so we could see what this graph looks like. But let's see, with our point, our critical point, we plug that in. It's going to be a mess, right? 125 over 12, that's our x. We're plugging in here, that's squared, plus 25 sixths cubed minus 5 times 125 over 12 times 25 6. And this is going to give us a value, and we'd want to see, is there a possibility of getting a larger or a smaller value. And certainly if you let y be 0, this part could become 0. Of course, that makes this whole thing 0 here. X would be positive. So we need a negative somehow. And just kind of looking through here, what if y was a really big negative value? And x were 0, that would make an easy calculation, wouldn't it? And let's make y like negative, because there's no constraints on this. Well, 10,000 is probably big enough. So we're going to cube it. Since x is 0, this would be 0, this would be 0, this will be negative 10,000 cubed, which a lot of zeros, is going to be bigger than this. Is going to be, sorry, smaller. It's going to be more minimum than this thing is. So it's just kind of looking, if we go out far enough, this thing is going to go off in a particular direction, can go off to basically negative infinity as we as you know, with x being 0 and y being more and more negative. So our minimum, our critical point, which is a minimum, is a local minimum, but not a global. So there's no global minimum. And since we don't have even a local maximum, we don't have a maximum. We have a saddle point, and we have a local minimum. So that's that one.